Hey, good morning, good evening, good afternoon, whenever you happen to be watching this video. This is Mrs. Brunk, and welcome to Algebra 2, Lesson 8.1, Graphing Simple Rational Functions. Today we're going to look at the most simple rational or fractional function, and we're going to take a look at making different changes to that basic function, which we call the parent function, and transforming it in different ways. And then finally we'll look at how we could model some real-life situations with some fairly simple rational functions. So we're going to first start off with a definition of what a rational function is. And so a rational function is a function of the form f of x is equal to p of x divided by q of x, where p of x and q of x are polynomials, and where q of x cannot equal 0. Now remember why that's important, because that q of x was the denominator, and you can never have a denominator equal to 0. The most basic rational function with a variable expression in the denominator is f of x is equal to 1 over x. Now the first question we'd like to answer when it comes to 1 over x is, what is the domain? And that's important because if we're going to graph these things, we need to know what things we can input in. And remember, our domain is our inputs. And so when I look at that, the only thing I can see that's going to really be a problem is 0 itself. I'm going to be substituting in values for x, and if I were to substitute a 0 in that denominator, it would make it undefined. Everything else seems absolutely just fine. So I want to be able to say, as my domain is that x cannot equal 0. So one way to say that is to just simply say it's all reals, and then except for x cannot equal 0. That's a little more informal way. Sometimes we use our interval notation, and we could say something like this, that it's negative infinity up to but not including 0, and then also positive infinity, 0 up to positive infinity, just past 0. So notice I used the weak brackets, or the parentheses, to show I'm not including 0, and then I could use a little union symbol in between. So basically I'm saying these two things together represent the interval notation form of the domain, which is basically everything but 0. Now the range I usually find it easier to establish once I see the graph, and so I'm going to go ahead and we're going to complete these tables over here to see if we can get a kind of a look of what this graph is going to look like. And so if I were to substitute in some negative values in for x, like say I plugged in -2, 1 over -2 is -1/2. And if I plugged in -1, 1 divided by -1 is -1. And if I substitute in -1/2, 1 divided by -1/2 is actually -2. Now looking at those same inputs but positive version, if I substituted in a 0.5 or a 1/2, that would be a +2. If I substituted in 1 for x, that would be 1 divided by 1, which is 1. And if I plugged a 2 in, that would be 1 divided by 2, which is 1/2. And let's see what that looks like when we graph those points. So -2 and then 1/2 would be right here. -1 and -1 would be right here. Oops, sorry. I just put those in the wrong spot. That was silly. Okay, sorry. -1, -2 and -1/2 would be here. -1 and -1 would be here. -1/2 and -2 would be right here. Then 1/2 and 2, so over 1/2 and up 2 would be right here. 1 and 1 would be here, and 2 and 1/2 would be right here. So that kind of looks weird. It looks like, how am I going to connect those points together? This is not like anything we've seen before, and that's because a rational function is not like anything we've seen before. We've been looking at polynomial functions. And in fact, in order to graph this without including an input of 0 for x, I actually would not be able to cross that y-axis. And then at that same time, that means since I can't substitute anything in that's going to make that fraction 0, I also can't get an output of 0, meaning I can't cross the x-axis. So what does that look like? It actually looks like a graph that looks like this. And it's separated, it's two separate branches that in this case are separated by the two axes. Okay? And this graph is called a hyperbola. And one of the things that's very characteristic of a rational function's graph is that it will have these separate pieces of the graph, or it's disconnected in some way. There are these places where the graph doesn't exist. We actually call those places asymptotes. They are basically parts of the graph or lines that the graph will approach but actually never cross. And in this case, the parent function has an asymptote here at the y-axis because we can never have an input of 0, and also on the x-axis because we can never get 0 out of that. There's nothing I could possibly plug in for x to make 1 over x be equal to 0. We could get really close to it, and you could see if I kept putting in bigger values of x that were positive or negative, I would approach 0 from either direction. On one side, I'd be approaching it from below, like say I put in a number, like say negative 10 way down here, then that value would be 1 over negative 10, the negative 1/10. That would keep getting closer and closer and closer to that x-axis but never cross it. The same thing on the other side. If I put, say, a positive 100 in for x, then that means down here somewhere, way down here, I'd plug in 100, and I'd get 1 over 100 or 1/100th, and that means this graph would just keep getting closer and closer, and the values, the output smaller and smaller, but they're never ever going to get to 0. So it approaches the x-axis but will never cross it, which is what an asymptote is. It's basically like a boundary line. It's a line that you can get really close to, but you can never cross it because it's a place that the graph is not defined at. So we've been talking about when we do look at graphs, we always talk about end behavior. So the end behavior, so if we look at as we're going to the right of this graph, so down here, if we're going to the right or towards the positive infinity for x, you can see that what's happening is that the graph is approaching 0. It's not ever going to get to 0, but it's approaching 0. And we're on the other side when I'm approaching, oops, I'm going to put my 0 back in. When I'm approaching the left-hand side, negative infinity, in other words, over here, you can see the same thing's happening. As I'm approaching 0, the graph is getting closer and closer and closer to 0, but it's never actually going to get there. Now, what about the behavior near the y-axis? So, in other words, like if we were saying as x was approaching 0 from the positive side. In other words, as I'm going this way, going towards 0 on the positive side of the graph is actually going up. It's going up towards positive infinity, as you can see there. And it's getting bigger and bigger and bigger. The smaller value I put in for an input of x, like if I put in, say, 0.00001, then if I divide 1 by that, it's going to make a very, very large number. So as I'm getting closer to 0, the graph is actually approaching positive infinity. And if I'm approaching 0 on the negative side, so in other words, over here, I'm getting closer to 0, going towards the y-axis, the graph is going towards negative infinity. It's going down, as you can see there. So that one's approaching negative infinity. And that's exactly why we have asymptotes at the x and the y-axis, because these are values, 0 on the ends, either end, and infinity towards the origin, towards the y-axis, that the graph is approaching but will never get to. So an important vocabulary word here is asymptote. And that word asymptote is basically a line that really is sort of like a boundary line in the graph that sort of divides it up. It's a discontinuity point of the graph. It's a place where it causes the graph to be disconnected and not flow continuously. Now you can always tell what the vertical, or that straight up and down asymptote is going to be by looking at the denominator of your function. So in this case our function was 1 over x, and because we knew that that denominator would be made 0 if we put 0 in for x. And that is exactly why we had a vertical asymptote where x is 0, which is on the y-axis. Now the reason for the horizontal asymptote was that because there was absolutely no way to make 1 over x equal to 0. I mean, even if the denominator was 0, it wouldn't equal 0, it would be undefined. It means it's trying to get to, as close as it can, to 0, but you can see on the graph it never actually gets there. Let's go ahead and turn the page. So we're going to start taking that hyperbola, that parent function, 1 over x, and we're going to make some changes to it, and we're going to see how that affects the positioning of the graph, maybe how steep those curves are, where the asymptotes lie, and we can see that it's going to really follow that pattern that we've seen with other kinds of functions, and how changing certain parameters will affect the look of the graph. So when graphing transformations of f of x is equal to 1 over x, in other words, that basic parent hyperbola, it helps to consider the effect of the transformations on the following features of the graph: the vertical asymptote, x equals 0, the horizontal asymptote, y equals 0, and 2 reference points, -1, and 1, 1. So looking down here at these graphs real quick, these are the parent functions, and on the graphs here you can see that the graph is divided where those asymptotes are, where x equals 0 and where y equals 0. In other words, the horizontal asymptote here is at y equals 0, and the vertical is at x equals 0. And those reference points we're talking about, they have on here, and that's because that's like basically where that curve turns. So that would really tell you how steep in that curve could be, or if, say, the point was way out here on a transformation, then that would make it less steep. And so watching that key point right there and where that goes to will help us to tell how steep to make these branches of the graph. So we're going to be watching that -1, which is right on the left-hand side over here, right there, and then 1, 1. And that'll help us to, as we do, like, say, our stretches and compressions, and how steep in the graph will be in that area. Now this right here is a general form, almost like how we've seen like vertex form or whatever with the other functions that we studied, and it shows you what applying some change to 1 over x will do to the graph. Now, just as in the other functions that we studied, multiplying, say, the whole function by a, some factor a, would cause it to have a vertical stretch. So that right there is going to cause you a vertical stretch. We know that if we add something off the end, that's going to cause a vertical slide. If we put a negative out in front, so in other words, if the a is now negative, then that means it's going to reflect it over the x-axis. But then anything that's going to cause a horizontal change is going to be found here, right on that denominator with x, because if we change x directly, we know that means that's going to cause a horizontal transformation. And all those same things apply. So if we wanted to slide left or right, okay, remember x lies to you, then we would just add or subtract from the x. Stretching or compressing horizontally. Just remember, though, that the scale factor that you'll see in the equation is always basically the reciprocal of whatever the scale would be. For instance, if I had 1 over 2, so b was 2, that would be 1 over 2 right here. And what that would mean is that that's going to cause a horizontal stretch. Even though I see in the equation a half, that 2 is really what the scale factor is, and that's going to stretch horizontally by a factor of 2, making the graph wider. So all those same rules apply, just like when we studied all the other polynomials. So let's see, if I looked at example A and I had to kind of speculate on what's going on here, I can see, first of all, that this plus 2 on the end, I'm going to guess that that's going to move this up 2. So it's going to take this parent function that's graphed, it's going to go up 2. And I think it's going to take the graph, and it's horizontally going to move it 1 unit to the right, because x lies to you, right? And I think it looks like it's going to do a vertical stretch, and by factor 3. And let's see what we could get that to look like on the graph. So first of all, if this is going to slide this right 1 unit, and if the asymptote is already at 0, x equals 0, but I move it to the right, my new vertical asymptote is going to move right over here to where x is 1, which makes complete sense, because if I put 1 in for x into that function, it would make the denominator 0, and that's exactly why that that vertical asymptote is there. Now the plus 2, because I'm basically taking that graph and sliding it up 2, that original horizontal asymptote was at the x-axis, right? It was at y equals 0, but now I'm going to slide everything up 2, so that means that asymptote's going to move up up 2 units. And so now it's going to be at y equals 2. And again, the vertical one is that x equals, let's see if I write over here, x equals 1. I better write that a little darker. So basically you can kind of think about this now as like your new x and y axis. These asymptotes are basically what, they're to you now what the x and y axis were to the parent function. And so now all that's left is to think about what would happen to that key point. Now that normal key point on the right hand side would have been over 1 and up 1 from where those asymptotes are. But now instead, because there's a vertical stretch of 3, it's going to be over 1 and up 3. So actually that key point, that part of the graph, is actually going to be right here. So if I kind of take the graph and go like that, that's actually going to be where that change in that shape is going to come from, is that vertical stretch. And so then on the other side, instead of going 1 to the left and 1 down, I'm going to go 1 to the left and 3 down now. So that'll put me right about there. And so then I can again draw that branch. And so now I can see that this graph is stretched a little bit vertically when I compare it to the parent function. It's a little steeper, and it's been shifted 1 unit to the right and 2 units up. So it basically just establishing where those 2 asymptotes are, like from the shift that's happening, the slides left or right or up or down, and then applying any stretch or compression to establish how close into those asymptotes the branches go. If there were, say, a negative out in front of that, then those branches would then flip across the horizontal asymptote and be in the opposite kind of new quadrants that have been established. Okay, let's go ahead and look at another example. Okay, so taking a look at this one, this time what kind of jumps out at me right away is always the thing added or subtracted off the end. So that subtraction of 1, I think that means that that's going to slide it down 1. So going down 1 would then take that horizontal asymptote, and instead of being at the x-axis, it's now moved down 1, and so that's going to make that be y equals -1. Now that x plus 3, I know that x lies to me, so that tells me that that's actually going to shift the graph 3 units to the left, so that means that instead of being at the y-axis, my new vertical asymptote is going to be where x equals -3, which makes sense because if I plug -3 in to that function, -3, it's going to make the denominator equal to 0 because it'll make that x plus 3 equal to 0. So now I've got my new basic parameters of where my graph, it's almost like my new x and y axes, where these asymptotes are, and now I can just look and see what other transformations happening. Well, there's this transformation right there, which is on the denominator with that. So now I know what that means is that's really like saying 1 over 1/2. So I think if there's a 2 there, it actually is going to be a horizontal compression of 1/2. So what would that do to the graph? Well, normally, the points would be like that 0.11 would be 1 point to the right and 1 point up, or like right there with respect to my new sort of axes. But now instead of going, since it's going to be a horizontal compression of 1/2, instead of going 1 right, I'm only going to go 1/2 right and up 1. And so going 1/2 right and up 1 is going to put me right about there. And so what that's going to actually do is going to make that branch be in closer to the asymptotes. Of course, it's still never going to touch it, but it's been compressed. So it's been compressed horizontally and pushed it in back closer. And then on the other side, instead of going 1 to the left and 1 down, I'm only going to go 1/2 to the left and then 1 down. And then again, that other branch would just be like right here. And so that kind of goes in line with the description that I just gave. That looks like a horizontal compression of 1/2, and you can certainly see that it's been shifted 3 left and 1 down. Now again, we don't have an example here that shows any kind of reflections, but if there was, say, a reflection, like say there was a negative on the denominator with that 2, that would just take, say this branch right here that's in the upper right-hand corner, and it would move it over here instead. It would just take that and flip it over, or Then it would take the one that's on the bottom and flip it over here, right? But otherwise it would have the same shape of the graph. And then really the same thing would happen if we reflected over the x-axis. So if there was a negative out in front, it would just flip-flop the branches, so they would still end up in those same quadrants. So really it would be hard to tell whether it was a reflection over the x-axis or y-axis, because it would really have the same essential effect. Okay, so as you can see in those two examples, if a rational function is written in that form, it actually is very easy to graph because it's very clear where the asymptotes are, and you can really distinguish what the transformation is, if there's any stretch or compressions, and what type they are. So what about if they're not in that form? So for instance, in this example A, you can see that, this one down here, you can see that this is written in a different form. So it has both an x on the top and an x on the bottom, and so then how do we tell, like, where's the asymptotes, or where are the asymptotes, excuse me, and so on. So this is the approach we're going to take when they're in this form. So when given a rational function of the form g of x is equal to mx plus n over px plus q, in other words, in the form like this is in, where m is not equal to 0 and p is not equal to 0. So in other words, when the numerator is not 0 and neither is the denominator, you can carry out the division of the numerator. So you're going to do division of the numerator by the denominator. And if we write the function in the form of the dividend equals the quotient plus the remainder divided by the divisor, we can actually put this back in that form that we're familiar with, which would be kind of like almost like a, not really a vertex form, but it's a form where we can just look at it and tell the transformations. So it'd be maybe the transformation form if we had to give that a label. So we're going to go ahead and try that with this one. So again, if it's not in that form, step one is we're going to try to divide. So we're going to take and divide the 3x plus 4, I'm sorry, 3x minus 4. By the x minus 1. Oh, I almost made that look like a square root sign. So again, when we divide with long division, we're going to see how many times does the first go into the first, and you can see that just goes in there 3 times. And then taking the 3 and multiplying it by x minus 1, I get 3x minus 3 that I'm going to subtract from above. And when I subtract 3x from 3x, they cancel. When I subtract negative 3 from 4, I get negative 1. And so now I can't go any further with my dividing, so that negative 1 is like the remainder. So if I wrote it in that form that you see right here, that it's the quotient, which is 3, plus the remainder, which is negative 1, over the divisor, which was x minus 1. Now you can see we have this written kind of in this form that we're used to. Maybe we would want to flip it around and say it's actually negative 1 over x minus 1 plus 3. But now we can see that this is a slide 3 units up. It's a slide 1 unit to the right. There's no stretch or compression, but the negative 1 there indicates that that would be a reflection over the x-axis. So let's go ahead and let's sketch that. So again, our horizontal asymptote is going to shift up 3 units. Our vertical asymptote is going to be what makes this equal to 0. So in other words, it's going to be 1. It's that slide 1 unit to the right there. And so now this is our framework to kind of graph this. We know that this is a reflection, and it's actually a reflection over the x-axis. So the part that I would have gone to the right one and up one, instead I'm going to go to the right one and down one, and that means I'm just going to put it down here. That branch is going to go down here. There's that reflection. And on the other side, I normally would go to the left one and down one, but now I'm going to go to the left one and up one. And that's going to put that branch in the upper left-hand corner now, and you can see that reflection. And so we were able to then take this by using division and writing our answer in this way, where we use the quotient plus the remainder over the divisor, and we were able to then rewrite this in a form that we could just read right from the equation what the shift was, and we could also tell if there was a stretch or compression or a reflection. Oops, let me redo that. And so this is our new function written in the correct form for g of x. Let's go ahead and try another one together, and then we'll leave one for you try. Okay, so looking at this example, 4x minus 7 over negative 2x plus 4, I really have no idea what the shift is. I don't know if it's slid left or right, up or down, if there's a stretch or compression. So I'm going to go ahead and divide the numerator by the denominator. So I'm going to divide 4x minus 7 by negative 2x plus 4. And so I want to see how many times does negative 2x go into 4x, and it goes in there negative 2 times. Negative 2 times negative 2x plus 4 would give me a positive 4x minus 8, and then I'm subtracting that. So change that to add the opposite. I'm going to change it to addition of the opposite of these, and that's going to make that a plus 8. Now I'm going to add, those cancel out. These add up to positive 1, so 1 is my remainder, so rewriting this in that other form would make a negative 2 plus 1, which is the remainder, over the divisor of negative 2x plus 4. Now if I really wanted it to make it look like that original general format, what I might want to do is flip it around so that the minus 2 is off the end, and then also take that denominator, and I'm going to factor out that negative 2. See how there's a common factor of negative 2? I could take out the negative 2 and make this x minus 2, and now I can really see everything that I need to be able to graph this, because I can see now that this is a shift 2 units down. I can see that this is a shift 2 units to the right. I can also see that with this negative 2 here, this has to be a horizontal compression of a half and a reflection over the y-axis. So that negative on the 2 means it's reflecting horizontally. And so to graph this, I'm just going to go ahead and put my asymptotes in. So the horizontal asymptote is shifted down to negative 2. I see that the vertical asymptote, which was at 0, is now moved 2 units to the right, so it's right here at positive 2. Oops. And now I see that it's going to be reflected over the y-axis, and also it's going to be compressed by a factor of a half, because you know the reciprocal of 2 is a half, right? So it's going to be compressed by half. So normally what would happen is I would go 1 unit to the right and 1 unit up, and I would be like right here, right? But instead, now I'm only going to go a half unit to the right and up 1, which would put me there. But then I'm going to reflect over the y-axis, which is going to take and put me right over here in this spot. So this one is going to disappear, right? And this is going to be my new point, and that means the graph's going to be over here like that. And then normally I would have gone to the left one and down 1, which would have put me there. But now instead I'm going to go to the left a half and down 1, which would put me there. And then of course I want to reflect over the y-axis, so that's going to move it over here. And so that's where my final point is now. It's going to be right over here, and that gives me my other branch of the hyperbola right here. So that's a pretty good sketch of what that's going to look like. And you could always confirm this by typing them in the calculator. Now, they're a little tricky to put in the calculator. I will tell you, when you do that, you have to make sure that if you have anything besides just a single term in a numerator or a denominator, you have to parenthesis the entire thing. So put a big set of parentheses around the entire numerator or denominator if there's more than just a single number in that position. So we'll look at that in class. We'll talk about a little bit more about how we could confirm by graphing those in our calculator. So we're going to leave this next one as a you try. You can either try it now, but we'll also go ahead and take some time and try it in class. So if you feel comfortable, you want to give this one a whirl right now. Otherwise, you can hold off, and that'll be how we'll start class, is working on this and other you tries. Let's go ahead and look at the last learning goal that we're going to look at in the video, and that's writing simple rational functions. given the graph. So if we know the graph, can we take the characteristics from the graph and turn around and write the function from it? And again, knowing that our base graph is 1 over x. And so let's take a look at this graph that's shown here. So first of all, I can tell that this vertical asymptote now is right here, and it appears to be moved to 1, 2, 3. It's moved 3 units to the right. Okay? So now I know that if it was moved 3 units to the right, and if I look back here at this general form, I know that it's moved 3 to the right, and I could do that by taking x and subtracting 3. That would move 3 to the right. Well, it looks also like the horizontal asymptote is moved up 4 units. So it's at y equals 4. And again, the vertical is at x equals 3. So that means if I'm shifting up 4, there must be a plus 4 on the end. Now the graphs are in the right quadrants. They're in the upper right hand and lower left hand, which means there's been no reflection. I can tell that. But now if I look at that key point right here, which normally is 1 to the right and 1 up, but I can see instead it's from where these asymptotes meet, it's 1 to the right and up 2. So instead of being just a plain hyperbola like this, it's actually going to be a stretched hyperbola by a factor of 2, because instead I went over 1 and up 2 to get to that point right there. And so that means this is multiplied by 2. So my function is g of x is equal to 2 times 1 over x minus 3 plus 4. Let's go ahead and look at one more. Now the one I'd like to do with you is number 11, and that's because this time it's indicating it's going to be a horizontal stretch or compression. So of course we know that's going to be a little bit trickier. The slides we can figure out just exactly the same, but then that horizontal transformation, or that stretch or compression, is going to be a little more complicated. So let's go ahead and take a look at what kind of slide has occurred. So I can see my 2 new asymptotes. Instead of being at the axes, I can see that the vertical one is at x equals 4. And I can see that the horizontal one is at y equals negative 3. So that means there was a slide 4 to the right. So if I kind of go back to my format, I know there's going to be an x minus 4. That's going to cause the right shift. I have a shift down 3, so that's going to be minus 3 in our function. And then when I look at the key points, so again, normally what would happen is I would go to the right one and up 1, but you can see where this point is right here. Now, instead of going to the right 1 unit from where those asymptotes cross, I actually went over a half a unit and then up 1. So what's happening is it's been compressed horizontally by a factor of a half. And what that means is that the b is a half. So that means that if I did 1 over 1/2, that value that I'm going to put in here in front of this x minus 4 is actually going to be 2. Okay? And so that actually reflects this graph. It's a slide 4 units to the right, it's a slide 3 units down, and it's a horizontal compression of 1/2. So g of x is equal to 1 over 2 times x minus 4 minus 3. Well, that does it for today's lesson. We're going to save those word problems for class, and we'll also leave this U-turn. I mean, again, you're welcome to try this if you're feeling confident and you want to give this one a try. Otherwise, we'll start off with a couple U-turn problems in class, and we'll wrap this lesson up with looking at some word problem applications. So thanks for coming to class.